This is the video for section 3.2. In this one, we're going to talk about applications of radian measure. The first one is talking about the arc length on a circle. We already talked about this when we defined our radian measure, but sometimes we're going to want to find out the arc length along a circle when we know the radius and we know the angle. The length s of the arc intercepted on a circle of radius r by a central angle of measure theta radians is given by the product of the radius and the radian measure of the angle. An easier way to say that is that s equals r theta, where theta has to be in radians. This is actually just a variation of the formula that we already had to find theta. Remember, that one was theta equals s over r. We could get that from this just by solving this for theta. Let's use this formula to find some arc lengths. If we have a circle with a radius of 18.2 centimeters, we want to find the length of an arc intercepted by a central angle having a measure of 3 pi over 8 radians. We could draw the picture of this. If we had our angle that measured 3 pi over 8 radians, let's say that angle is somewhere around there, and our circle has a radius of 18.2 centimeters. So that would mean that from here to here would be 18.2 centimeters. What we're trying to do in this problem is find the arc length from here to here. So the distance that we'd actually travel along the circle to get from there to there. Since this angle is already in radians, then all we have to do is use the formula. We're putting in our 18.2 centimeters for r, and then our radian measure of the angle. I'm going to write the units for the radius, but not for this, because remember, the radians really isn't a unit like other units. And if I do this, then my unit will end up being in centimeters, and that's what I want. I'm just going to put this in my calculator, do 18.20 times 3 pi divided by 8. That's going to give me approximately 21.44 centimeters. So that means that this distance from here along to here is going to be just a little bit bigger than the radius of the circle, which was 18.2. So this is going just a little bit farther than the radius of the circle. For this one, we've got the same idea, only this angle is measured in degrees. So we could draw this on our picture up here. 144 degrees would be somewhere over here. So now we're looking at the length along the circle from here all the way over to here. That distance along the circle from there to there. To do this, to use the formula, we have to convert our degree measure to radian measure. We're going to take our 140 degrees times pi over 180 degrees so that our degrees cancel out. I'm just going to leave this as 144 pi over 180. Because I'm going to do this on my calculator anyway and get an approximation. Now I'm using my formula to find S. I'm putting in 18.2 centimeters for the R, and here's my radian measure of my angle. I'm just going to work out this whole thing on my calculator. That's going to give me approximately 45.74 centimeters. So our arc length up here is more than twice what our radius was. So it's going a little bit more than 1 radian to get here, and this is more than double what our radius is. The next application we can do with this is to find an approximate distance between two cities using their latitude. This can work if you have two cities that are approximately due north or south of each other. What we're looking for is the difference in their latitudes. They're both north of the equator. So this one has a latitude of 34 degrees north and this one has a latitude of 40 degrees north. So the difference between those angles is actually 6 degrees. What we really want to know is the distance along the circle, which is the outside of the Earth, from here to here. So really what we're looking for is the arc length. So we're going to take the distance between those two angles as our angle measure. That was in degrees, so we have to convert that to radians to use it in our formula. Again, I'm not going to try and simplify this because I'm going to put it in my calculator eventually anyway. Now I'm just using my formula, and here it gives me the radius of the Earth. That's 6,400 kilometers approximately. I'm plugging that in for my R, and then I'm putting in my angle measure in radians for the theta. And if I multiply that out on my calculator, I get approximately 670, and my units were kilometers. And this one, since the radius value here had 2 significant digits, I rounded this one to 2 significant digits also. In a lot of these problems, it doesn't tell you whether to use significant digits or how many places to round it to. But if you're doing problems on MyMathLab, it's very specific about what type of rounding to use. Let's look at another example. In this one, we have a rope that's being wound around this drum. We know the radius of the drum, and the question here is if we rotate the drum by 39.72 degrees, then how far will the rope be wound around it? So really what we're trying to find is the length of the rope from here to here, and that's an arc length. So we're still using our formula S equals R theta, and we're trying to find the S. The R is 0.8725 feet. For the theta, we need to convert this degree measure to radians. I'm just going to leave it like this to put it into the formula. So we would have our 0.8725 feet times 39.72 pi over 180. Putting that in my calculator. This one, my values here were 4 significant digits, so I'm going to round this to 4 significant digits, and that gives me 0.6049 feet. Now, I do always want to look at the picture, if I have one, to make sure that my answer makes sense. In this one, the radius of the circle was 0.8725 feet. If you kind of compare that to the length up here, if we assume that this was drawn approximately to scale, then this does look like less distance than this was. So that makes sense that it's 0.6049. In this example, we have 2 gears. The smaller gear is driving the larger gear. The question is, if we rotate this gear, then what angle is that going to make the larger gear rotate? We're going to rotate the smaller gear through an angle of 225 degrees. In this case, we have the radius of the smaller gear, and we know the angle that we're going to rotate it through. If we look at our arc length formula, we've got the radius and we've got the angle, so we can find the arc length. In other words, if we rotate this 225 degrees, about like that, we can figure out the arc length that this smaller gear is going to go through. Now we do have to convert our angle measure to radians. We're using the radius of the smaller gear. If I work that out on my calculator, I'm going to get an answer like this. This one, I'm taking it out to as many decimal places as I can because I want to use this value in another calculation. So I don't want to round this one if I possibly can. The question is, if this is our arc length, we want to figure out the angle that would make the larger gear go through. What you can think about is that while this smaller gear is rotating, it's making the larger gear rotate, and that larger gear is going to rotate with the same arc length that we had here. So then the question is, if this larger gear rotates with an arc length that's the same as this, what angle is that going to translate to for the larger gear? So this time we actually know the arc length, and we know the radius of the larger gear. What we're trying to find is the angle. So the thing that we don't know in this formula is the theta. We just want to solve this for theta, so we're just going to divide both sides by the 4.8 centimeters. That's going to give us theta equals this value. This is in radians because we were using this formula. To make sense in this problem, since our original angle was in degrees, we want to take this and convert it back to degrees. So we're going to take this value and multiply it times 180 degrees over pi to get this back to degrees. We get a degree measure of approximately 117 degrees. In other words, if we rotate this one 225 degrees, that's going to cause this one to rotate about 117 degrees. Another type of application we can do for this is that we can talk about a sector of a circle and find the area. When we talk about a sector of a circle, that's the part of the inside of the circle that's intercepted by a central angle. If I draw a central angle in here, then what I'm looking at is this sector, which is this inside part of the circle. Since this is something in 2 dimensions, then instead of talking about a length, we can talk about the area of this sector. And here's the formula for that area. Just like for our arc length formula, in this formula the theta has to be in radians. Let's do an example where we use that formula. In this picture we've got a center pivot, and we want to know what happens if we use the center pivot on a sector of a field with an angle of 15 degrees and a radius of 321 meters. We want to know how much area that irrigation is going to cover. What we're trying to find is the area of this region in here. We know our angle is 15 degrees. To use this formula, we have to convert this to radians. The other thing we need for the formula is the radius. That's going to be 321 meters. Now this time they're asking for the area, so we want to be sure and use the right formula. This formula is 1/2 r squared theta. We can put in 321 meters for the r, and then our theta in radians is 15 pi over 180. I did all of this on my calculator, and I ended up with 13,488. And to put the units in for this one, we started out with meters here and we squared them. So the units in this answer are meters squared, or you could say square meters. That makes sense that it's squared because this is talking about an area which is 2-dimensional.